Lesson 11.8 is about geometric probability. Okay, probability is the likelihood that an event will occur. And we're going to set up probability as a ratio of either lengths or a ratio of areas in this little lesson because we're going to be talking about geometric probability. And the probability that something will occur we can state as a fraction or as a percentage. So let's say that I have this segment that's here at the bottom, segment AB, and I'm just going to randomly close my eyes and put my finger down on the segment and call wherever I put my finger point P. Now, the probability that P is on somewhere on AB, but the probability that it happens to be on AC is going to be the ratio of the length of AC over the total length of the segment AB. Okay, so I think that makes logical sense. In this picture, it looks like it's probably about 2/3 of the probability is probably about 66–67% that the random point would be on AC, because AC is about 2/3 of the length of AB. Okay, now with respect to area, suppose that I have that I'm referring to this kind of blob down here at the bottom of the page, and I have the big area that's enclosed by the blue line is area S, and inside of area S is a smaller area that's enclosed in green that's area R. Now if I throw a dart that's going to hit somewhere inside of region S, what is the probability that the point where the dart hits, which is point P, is inside region R? So the probability of that is the ratio of the areas. It's the ratio of the area of region R over the area of region S. And again, I think that that makes logical sense. Obviously, the area that's inside of S but outside of R is much bigger than the area inside of R. So it's a, definitely less than 50%. Maybe this looks like it's maybe about a 1/4 or 1/5 ratio of the area of R to area of S. So that's basically how we figure out probability of a random point being picked inside of a length, segment length, or inside of an area. Okay, so in this first example, let's say that we have this long segment at the bottom, AF, and we are given that AB, BE, and EF are all the same length. So if the entire segment is divided evenly, and those are all the same length, then each of those segments is 1/3. Okay, so BE is 1/3. And then we're told that BC and CD and DE are all the same length. So basically, each of those is 1/9. So I'm going to erase the 1/3 here and make each of those 1/9. And this will help me to find the probability. I'm going to pick a point at random, and what's the probability that is between point A and point B? Well, that's a probability of 1/3, because AB is 1/3 the length of AF. Okay, I'm going to pick a point on AF at random. What's the probability it is between B and C? Well, that is 1/9. It's 1/3 of 1/3. And then what's the probability that the point is between C and F? So between C and F, I have EF, which is 1/3, and then I have CD, which is 1/9, and DE, which is 1/9. Oops. So I have 3/9 plus 1/9 plus 1/9, or 5/9. Probability that the randomly picked point is between C and F. So that's how I would approach a problem like that. Okay, now for a challenging area problem. I have here sort of a square inscribed inside of a circle, and the circle is inscribed inside of another square. And I want to know, if I throw a dart, what is the probability that the dart will land inside the purple shaded area? So what I'm looking for is I kind of want to frame what area I'm talking about. Okay, definitely the denominator of the probability problem is going to be the area of the big square, the total area. And the purple shaded area is actually the area of the circle minus the square that's inside of it, that's in the position like this, like a diamond. So that would leave the ratio of the purple area to the total area of the outside square, because we're assuming that the dart's going to hit somewhere inside the big square. So I might suggest a strategy for doing this. Instead of looking at the whole circle and the whole big square and the whole small square, I'm going to divide this into quadrants. And I know that one quadrant is the same as any other quadrant. And I'm just going to look at this one up here in the top right corner. Because if I can find the probability that just looking at that top right square, the probability that the dart will land in the purple region, it'll be the same for the entire diagram. So I'm going to call the sides of that top right square x. Okay, so in this case, the big square is going to have an area of x squared. So that's going to be my denominator. And next I want to figure out the area of the circle. So the area of the circle, in this case it's a fourth of a circle, isn't it? The area of the fourth of a circle, the radius of the circle is x. See, if we look at the length of the radius from here out to the side is x. It's like the side of that little square. So I could say the area of the quarter circle, actually, so 1/4 of the area of the circle, is 1/4 times pi times the radius, which is x squared. So let's just call that x squared over 4 times pi. Okay, now I'm subtracting from it. In this case, I'm actually just subtracting the triangle. So the triangle, let's see, it's going to be, this is a right angle because that's a rhombus. So that triangle, the area of that, it's a right triangle, is 1/2 base times height. So 1/2 base of x times height of x. So this is 1/2 x squared, or x squared over 2. So that is like that. Now we've got to simplify this. So the first thing I'm going to do is put both of the denominators in the numerator of this fraction over 4. So I'm going to multiply this one on the right by a 1 in the form of 2 over 2. So now I have x squared over 4 times pi minus 2x squared over 4, and that is still all over x squared. So continuing on, I now have x squared times pi minus 2x squared all over 4, and that's divided by x squared. So let's call that times 1 over x squared. And I'm almost done here. If I factor out the x squared in the numerator, I'll have x squared times pi minus 2 all over 4 times 1 over x squared. So I'm going to cancel. I have an x squared over an x squared that cancels, and I'm left with the ratio pi minus 2 over 4. And if I enter that on my calculator, pi minus 2, so about 3.14 minus 2 divided by 4, I get about 28.5%. So I could just round that to be about 29%. And if that's the probability in that one quadrant, that's the probability in the whole thing, because every quadrant is identical. So the probability that I hit a dart inside the purple area in this particular diagram is about 29%. And that's a good challenging problem where you use a lot of algebra and reasoning. And good luck on solving problems like this.